We'll continue our discussion on dynamic optimization problem. The problem we were looking into was as follows. We have xt plus 1 equals to ft xt ut and my cost function, which I am going to denote by j of u vector. So, is equal to ct plus 1 xt plus 1. T goes from 1 to capital T. Did we start t equals to 1 or t equals to 0? Can you check in the notes from the previous lecture? Did t start from 1 or 0? 0? Okay. And I am going to define this vector u by u0, u1 all the way up to ut, the vector x by x0, x1 all the way to xt plus 1. And there was another function we introduced, which is xt equals to phi t of the u vector, which comes from composition of f1, f0, f1, f2 and so on. So, this was the problem statement we were discussing in the previous class. Currently, we are assuming that x and u can take any values in R n and R m. So, it is all unconstrained optimization at this point of time. And what we want to do as always is to find the necessary condition for optimality. We want to find out what the derivative of j of u is. Okay. So, our goal today, calculate the gradient of j of u. Given that it is an unconstrained problem, what is the first order necessary condition for optimality? It's that this should be equal to 0, right? That's what the first order necessary condition for optimality is going to look like. But you know, this is both obvious but somewhat abstract, because remember in the previous class we had talked about this u bar could be 1.8 million dimensional vector, right? So, saying that this 1.8 million dimensional object is going to be equal to 0, I guess there has to be a better way to write that down. So, that is what we want to do today. Any questions so far? What should we do? I want to find out what the expression for this gradient of u ju is going to be like. How would you go about solving this problem? What is the simplest case? So, remember this u arrow comprises of u0 all the way up to ut. This is in R m times t. I mean, I should probably write it as a vector, not as a matrix. Let us try to just take the derivative with respect to ut first. Okay. what is this derivative? This seems to be composition of two functions. What's the derivative of composition of two function? Excuse me. Anyone remembers? Derivative of composition of two functions?
You have to do the chain rule.
Yeah, the chain rule. What is the chain rule for this?
So it'd be like dc dut or dut dc.
So we do the derivative of the inner function first, and then we multiply it with the derivative of the outer function. So the derivative of ft with respect to ut. So this is a matrix. What's the dimension of this matrix? Rm cross n, and this is a vector Rn cross 1. Remember, x is an Rn, u is an Rm. So we get a vector Rm cross 1, which is what we expect this vector to be. Any questions?
Why the second derivative is with respect to x?
Because ct plus 1 is a function of xt plus 1, right? So ft maps, f capital T maps xt cross ut to xt plus 1. So the derivative is xt plus 1 here, and then this is the derivative with respect to ut. This is just chain rule, okay? We studied chain rule in lecture 2 or 3, so I'm just invoking that same chain rule here. So this is fun. Let's try to do ut minus 1. The gradient with respect to ut minus 1. Okay, so I have gradient of ut minus 1, ct plus 1, ft minus 1, xt minus 1, ut minus 1, ut. What is the derivative of this? Now I have to apply the chain rule again. So this is ut minus 1 of ft minus 1 times gradient of xt ft times gradient of this is a vector in R m cross n. This is a vector in R n cross n. This is a vector in R n cross 1. Okay. Do you see any pattern coming out of these expressions?
The first and last are always the same. They're the same
Right.
function.
And what about the middle?
It's always an n cross n.
Right. So what should the gradient of ut of j looks like? It's a bunch of matrices that are getting multiplied. What are those matrices?
This is just for a generic ut.
So I have ut minus 1 here, I have ut minus 1, ft minus 1. So this is ut of ft, gradient of ft with respect to ut. Then you look at the next state, and this is xt plus 1 ft plus 1. I'm going to keep multiplying xt plus 2 ft plus 2 x capital T f capital T xt plus 1 ct plus 1. That's the derivative. Yes.
CP plus 1 is the cost vector, which is a constant, right?
This is a constant, yeah. I mean, not constant, but it's a function of xt plus 1. This is a function of xt plus 1. Okay. So every time you make a change in your action at time t, it leads to a ripple effect. Okay. So how is that ripple effect felt to the terminal cost? So it changes the way xt plus 1 is, then xt plus 1 change influences xt plus 2, then xt plus 2 changes xt plus 3, and so on, and then finally xt plus 1 influences the ct plus 1. So this is basically a ripple that is going through the time. So any small change in ut here will pass through this ripple effect and then eventually influence ct plus 1. So that's what this expression is doing. So one thing you will notice is many a times optimization problems have a specific structure. So in this case, the action influences the state influences the cost. So that's the special structure here. And what we are doing is exploiting this special structure to simplify the computation of gradient of J. It's always good to exploit the structure in the optimization problem. So that's what we are trying to do here. Any questions so far? All of you are clear how I got this statement? You keep going through this process again and again, and you will see that this is the structure that will emerge out of it. And then you can use the principle of mathematical induction to prove that this is indeed the gradient of J with respect to ut. So J is called the performance index. J is called performance index, or it's called cost functional. You can use any of these terms depending on which book you are reading. You will find different names for this function J. So J acts on the entire sequence of u and gives you what the total cost of the control action is. Now I am going to rename some variables here or some matrices here. So let's try to rename them. I am going to call this pt plus 1. I am going to call this pt. I am going to call this pt plus 1, small t plus 1. So what do I get with this definition? These vectors pt would be called co-state vectors. Can someone tell me how does PT evolve? What's the evolution equation of PT? What's the dimension of PT?
N by N, or N by N.
N cross 1. So this is N cross 1. Then you multiply it by a matrix, N cross N matrix, so you still get N cross 1, and so on and so forth. What's the evolution equation for PT? So PT equals to no, that we have already written it down. What is PT equals to? I want to get the expression.
Derivative of x.
Xt ft times pt plus 1. This is known as adjoint equation. Okay. So I wanted to compute, my goal was to compute the gradient of u of j of u. Have we been able to accomplish this? So here is what we have arrived at so far. So this is my performance index. This is my state evolution equation. So this is how the state evolves. What I got is a adjoint equation which is initialized as gradient of xt plus 1 ct plus 1, and then the adjoint equation actually runs backward. So if you look at it, this equation runs forward in time. Okay, so you start with x0, you apply u0, you get x1, then you apply u1, you get x2, and so on and so forth. So this one runs forward in time. This one actually runs backward in time. So it starts with pt plus 1, capital T plus 1, and then you get p capital T minus 1, and so on and so forth, all the way up to p0. Okay. So gradient of u of j is actually gradient of u0 f0 times p1. Is that right? Yeah. Gradient of u0 f0 times p1, gradient of u1 f1 times p2, gradient of ut ft times pt plus 1, and then pt plus 1 equals to gradient xt plus 1 ct plus 1, and pt equals to gradient xt ft times pt plus 1. That's what my derivative of j looks like. Any questions? Questions? No? How do we run the gradient descent algorithm in this case? What would be a way to run a gradient descent algorithm? So first we start with some arbitrary initial condition, which is arbitrary sequence of vector u. Then we calculate, we do the forward propagation of u, we calculate the entire xt. Then we do a backward propagation of adjoint equation starting from p capital T plus 1 all the way up to p0. Then we compute this matrix, because now we know everything within this matrix. I know what p1, p2 all the way up to pt plus 1 is. I can compute the gradients. I can evaluate it at xt and ut, corresponding xt and ut. I get the entire gradient and then I subtract it from u using some step size selection rule, typically a constant step size or a decreasing step size, and then you get ultimately this gradient would converge to 0 and you are at a candidate for an optimal solution. Okay, that's what people do. That algorithm is known as backpropagation algorithm. Many of you might have heard about it in the context of training neural network. So we'll derive that algorithm using this expression on Monday. Okay, we'll derive the backpropagation algorithm. One thing to note is that this particular theory was developed in 1940s in Russia. Okay, so that's what we'll talk about the theorem in a bit. But this algorithm was actually rediscovered multiple times in different forums, right? So neural network people came up with the backpropagation algorithm. Controls people came up with the same algorithm, but they called it this adjoint equation and co-state vectors and all that. So there are different names in different contexts, but ultimately the math is the same. The math doesn't change, thankfully. So we'll talk about it on Monday. So now let's go back to the original problem. So now I want my j of u to have a running cost component as well. So I have a running cost and I have a terminal cost. I know how to solve the terminal cost problem. How do I solve the running cost problem? In other words, how do I convert the running cost problem into a terminal cost problem? Is there a way to do it? So here is what I'm going to do. I'm defining a new state which is xt and yt. And I'm going to set y0 equals to 0. Okay, we have seen many algorithms where we had to augment the state space, right? You've studied so many algorithms in Nesterov gradient descent, Nesterov's accelerated gradient method, in method of multipliers. We always had to augment the state space in order to study the convergence. We are doing the same thing here. We are augmenting the state space. This was my original state space. I augmented it with another state which is keeping track of the running cost, the cost accrued until now. So this is total cost accrued until time t plus 1. Wonderful. So what does the j of u become? Ct plus 1 xt plus 1 plus yt plus 1. I can call it c tilde t plus 1 x tilde t plus 1. Great. So now I have been able to transform the running cost problem into a problem that I already know how to solve. Okay? Any question with this transformation? So this is a technique we have been using all along during the optimization class. There is something I know how to do. I'm seeing a new problem. I'm trying to massage the problem so that it becomes similar to the problem that I've already seen. Okay, so we are able to do this here by augmenting the state space, keeping track of all the costs that have been accrued until now, and then add the terminal cost with the cost that has been accrued until now, and therefore convert it into a problem that I already know how to solve. Now what we want to do is go through the entire derivation all over again and then try to see what the co-state vectors look like and what the gradient of ut of j looks like. And I want to write it, where should I write it? Okay, let's do the adjoint equation first. So the forward equation is already on the board. The forward equation is this. Terminal cost is this. So I need to know the adjoint equation. So my pt plus 1 is p tilde. So I have to use p tilde because this is all under the new state space. Okay, so this is gradient of x tilde capital T plus 1 c tilde t plus 1. Can someone tell me what this is going to be? So this is this vector has two parts, xt and yt. So I have to differentiate this with respect to xt. What is this equal to? What is gradient of c tilde with respect to xt plus 1? This is, remember, this is my c tilde t plus 1. What's the gradient with respect to xt plus 1? Okay. It's just the gradient of ct plus 1 with respect to xt plus 1, and that's because this variable is independent of xt plus 1. So I don't have to take any derivative. I mean, the derivative of yt plus 1 with respect to xt plus 1 is 0. Now in the second part, I need to find the derivative of c tilde t plus 1 with respect to yt plus 1. So that is equal to 1. remember that yt plus 1 is a scalar. Okay, so yt is in R. So this is going to be just 1, and this one is in Rn plus 1. I am going to call this f tilde t x tilde t ut. So in order to find out what the co-state vector looks like at time t, I need to find the gradient of x tilde t f tilde t. So let's try to find that out. What should this be equal to? This would be gradient of xt ft gradient of xt ct, and then I have to take the derivative with respect to yt here. So gradient of, so ft doesn't depend on yt, so this term doesn't depend on yt, so that's 0, and this one depends on yt but the derivative is just 1. So I get this matrix. So this is derivative of the term with respect to xt, these are derivatives with respect to yt. So derivative with respect to xt, you have ft that depends on xt, and then you have ct that depends on xt. So those two terms come here, and then I have 0, 1. This 0 is actually a 1 cross n vector. So it's not like a single scalar 0, it is like 0, 0, 0, 0, 0, and that's because I'm taking derivative with respect to yt. That's because each of these ft, so ft is, this is a vector in Rn. So each of these vectors do not, each of the element of the vector does not depend on yt. So that's why I have n cross 1, 0 in the row vector format. Okay, so now what I need to do is I need to find out what this adjoint equation looks like. What is the value of pt? So pt is gradient of, or I should say, should I say p tilde t? P tilde t is gradient of x tilde t f tilde t times p tilde t plus 1, and this would imply so another thing you will notice here is, if you look at this, this is the vector but this is 1, and then you have 0, 1 here. So the second part of this co-state vector is always going to be 1. Okay? So that's because this 0, 1 gets multiplied by this vector, but the second part is only 1. So this part of the co-state vector is always going to be 1. So that gives me gradient xt ft multiplied by pt plus 1 plus gradient xt ct, and then 1. That gives me the adjoint equation. Oh, I also need to find out gradient of u0 or of f tilde 0. So I need to find this term. What should I erase from the board? I want to erase something. I'm trying to figure out what should I erase, what is not going to cause any problem. Okay, let me erase. Awesome, I have some white space. So now I need to find out, this is the only matrix that is missing right now. So gradient of ut of f tilde t and then this is 0 and then this is 0. No, I don't think I need to have 0, 0 here, right? Ut is just a single vector, okay. So then I have gradient of ut, this is equal to what does that give me? Any thoughts? What does this give me? So this is this matrix which gets multiplied by this particular vector. So I get gradient of ut ft times pt plus 1 plus gradient of ut ct. So that completes our derivation for the one with the running cost. So this was my f tilde. I took the derivative with respect to ut of f tilde, and then I need to multiply it by p tilde t plus 1 and I get this expression. So finally, going back to this particular statement, what do I need to add here? So I have gradient of u0 p1 plus gradient of u0 c0, gradient of u1 c1, gradient of ut ct. So that gives me the gradient of j with respect to u, and the only way I have to change the adjoint equation is pt equals to gradient of xt ft pt plus 1 plus gradient of xt ct. That comes from here.
That's the adjoint.
That's the adjoint equation. So this is the adjoint equation. So we started with a very complicated problem where I needed to solve this, I needed to minimize this performance index over a 1.8 million dimensional vector. That seemed very complicated and time consuming. So I needed to simplify this whole expression, something that can be done easily. So what we did was we came up with this function phi t, which maps the trajectory of u to the trajectory of x. Then we started taking the derivative with respect to u0, u1, u2 and so on. And finally, we are able to do a lot of mathematical calculation in order to get to this final expression of what the gradient of j with respect to u looks like for the cost with unbounded state, unbounded action, running cost, terminal cost and a state transition function. Okay? That is what we were able to do. So the necessary condition for optimality says that this particular thing has to be equal to 0. So let us write down what Pontryagin said back in 1948. Okay, I am going to erase this side of the board. Any questions on this side before I erase it? No questions? So I am going to take you back to Russia in 1948. So Pontryagin did this whole derivation in the continuous time, but continuous time is a bit complicated. He was a mathematician, so he could do continuous time. I am not a mathematician, so I only do discrete time. So discrete time is much easier to understand. Continuous time is a bit more complicated. So what was his result? I am going to define a Hamiltonian h of xt ut pt plus 1 equals to this is how I define my Hamiltonian. It's a function of the current state. Oh, this is also h should be a function of time as well. So ht Hamiltonian at time t is a function of the current state, current action and the future co-state vector. Its future co-state vector transpose ft. So remember, this is a vector in Rn, this is a vector in Rn and this is a scalar. So what I get is a scalar. This whole thing is actually a scalar. And so his result was, let u star be optimal. So I want to say like be a minimum x star be the corresponding trajectory then gradient of ut of ht evaluated at x star t u star t pt plus 1 star is equal to 0, where p capital T plus 1 equals to gradient of xt plus 1 ct plus 1 and pt equals to gradient of xt ht xt star ut star pt plus 1 star. This is the adjoint equation. So this theorem is sometimes called Pontryagin maximum theorem, sometimes it's called Pontryagin minimum theorem. We are doing minimization of cost, so we will always call it minimum theorem. Sometimes you do maximization of reward, and then it's called a Pontryagin maximum theorem. Okay, so we'll always consider the minimum theorem because we are doing minimization of cost. And it turns out that this expression is actually exactly equal to so gradient of ut of j is exactly equals to gradient of ut of ht. Okay, that's the cool thing about this definition Hamiltonian. So you take the derivative of Hamiltonian with respect to xt, you get the co-state vector. You take the derivative of Hamiltonian with respect to ut, you get the gradient of the cost functional with respect to ut. Any question? No questions? Awesome. Either everybody understood everything or nobody understood anything. That's the only two outcomes that can happen when there are no questions in the class. I guess I'll believe that everybody understood everything. Okay, that makes my life easy and that makes your life maybe easy, maybe difficult, I don't know. Is there some other name for co-state vector? What does co-state vector correspond to? Something that we already know. Okay, so let's try to think about it. What is this co-state vector? Here is a different way to look at it. It's not the original derivation. So original derivation is what we did in the classroom. Let's try to think about it in some other manner. So I want to minimize ct plus 1 xt plus 1 plus summation ct xt ut, t goes from 0 to capital T, such that ft xt ut minus xt plus 1 equals to 0. And I am minimizing over the entire x vector and u vector. But I have this constraint. What does this lead to? It's a constrained optimization problem, right? What's the Lagrangian of this constrained optimization problem? Lagrangian is a function of x, u and lambda. So this is for all t, by the way. So this would be Ct plus 1 plus summation Ct plus, let's say, lambda t transpose Ft minus xt plus 1. Oh, there has to be a summation here also. And what does the Lagrange multiplier theorem say? If x star u star is optimal and regular, then there exist Lagrange multipliers lambda such that the derivative of this with respect to x goes to 0. At the star. That comes from Lagrange multiplier theorem. It turns out that this lambda star is exactly equal to the pt star here. Okay? So if you view it as a constrained optimization problem, you will get exactly the same set of necessary condition for optimality. And there the Lagrange multipliers would be exactly equal to the co-state vectors. So I leave this as an exercise. We are already out of time for today, but I leave it as an exercise. There are two things to check. One thing which is very easy to check, or I shouldn't say easy, actually it's quite a tedious calculation, but you will notice that every point x vector and u vector is a regular point. Okay? That's just the nature of this particular constraint. So every point is a regular point in the space. So therefore the regularity thing doesn't appear. So x star u star will be regular. Therefore the Lagrange multipliers lambda arrow will always exist, and it will satisfy this expression, and this expression is exactly equal to the gradient of ut of ht and gradient of xt of ht. So see, this gradient of Lagrangian is with respect to x and u. You will get exactly these two things, which is equal to 0. So you will get something like pt minus this gradient is equal to 0. So you will get something like this, and you will get something like this is equal to 0. So you can derive the same result, Pontryagins result, using Lagrange multiplier theorem, or you can use this complicated algorithm that but complicated stuff we did today to arrive at the same conclusion. So there are many ways to get to reach the same conclusion that we have arrived today. So in the next class, I am going to apply this approach to talk about backpropagation algorithm for training neural networks, and then we'll apply it to linear quadratic regulator problem and try to solve some simple problems. Thank you so much. We'll see you on Monday. Have a great weekend.